we're going to talk about Abel's lemma and Abel's theorem right now. And basically it says that, you got this conditions, this sequence has to be decreasing non-negative. You have to have a series with bounded partial sums. So when can you use this? You can definitely use this when the series converges. Because if it converges, then it's going to have bounded partial sums because it has a limit. When the series converges. But there's also a case where you can use it. I'll give an example, and we're going to be fleshing out this example. There's another case where you can use it, and you can't use it, though, when this thing just flat out a sub n goes to plus or minus infinity. For instance, you can't use it on the harmonic series because that's not going to have bounded partial sums. But here's a second example where you can use it. How about negative 1 to the m plus 1, which equals, you think of this as 1 minus 1 plus 1 minus 1 plus 1 minus, and it has a sequence of partial sums is going to be 1, 1 minus 1 is 0, 1 minus 1 plus 1 is 1, 0, 1, 0. And so notice that this is always less than or equal to 1, so I can set that equal to my a. So let's do kind of a full-on example. Let's formalize this. A sub n equals negative 1 to the m plus 1. And here, I already told you a is equal to 1. And I can let my b sub n equal, how about 1 over n, like so. Well then, so the way to think about Abel's lemma is Abel's lemma is a substitute for triangle inequality. Triangle inequality. My pen isn't writing all this smoothly right now. Putting in green because it's really important. So what we really want is we want to figure out a sub 1 plus plus a sub n is less than or equal to something. Well, you normally do it with a triangle inequality. So for this particular case, you'd want to say, right, a sub 1 plus a sub 2 plus plus absolute value of a sub n. That's the triangle inequality. But in this particular case, notice that the absolute value of all the a sub I are 1. So this is equal to 1 plus 1 plus plus 1 equals n. This is going to be basically unbounded. So this is a little bit of a problem. So we don't actually have a bound in this case. So what we do instead is we use Abel's lemma. What we can say is that, well, we can't get this exactly, but I can know that a sub 1, b sub 1, plus plus b sub n, a sub n, which equals in our case, well, a sub n is 1 times 1 over 1 plus negative 1 times 1 over 2 plus plus or minus 1 times 1 over n. I know that this is going to be less than or equal to 2 times a times b1. That's what Abel's lemma says. So even though I can't use a triangle inequality here, if I can cleverly find some bn that work, then it'll still be fine because they'll just give me 2 times 1 times b sub 1 is 1, so that gives me 2. This thing is less than or equal to 2, which is helpful. In particular, in the proof of Abel's theorem, what they do, and this is tough to tease out, is that the a sub n, what they're summing, is equal to a sub m plus n r to the m plus n, and then the b sub n are equal to absolute value of x over r to the m plus n, sorry. So these are the two sequences that they're using to prove, and you notice how it's very helpful there. End of screencast.